Hello boys and girls, I'm Madam Yap from New Dawn Enrichment Private Limited. Today's lesson is on magnets. So what is a magnet? A magnet is an object that is made of a material that exerts a magnetic force. So it has a north pole and a south pole. Like in this case, we have a bar magnet, north and south pole, you can see, north, south. And we have a U-shaped magnet. Again, we have the north pole and the south pole. We even have ring magnets. So this is a ring magnet. So you were wondering where the poles are. Ring magnet, and you can see that they all are attracted to the flat surfaces. So the flat surfaces are the poles, this side and the other side. Okay, this and this. These are the poles of the ring magnet. And I've got disc magnet, and similarly, the poles are also on the flat surfaces, either north and south or south and north. Okay, so the poles are on the flat surfaces of the disc magnet. Okay, so these magnets are made of magnetic materials, so they can be iron, nickel, cobalt, steel. All right, and we can see that the opposite poles of a magnet attract each other. So the north is attracted to the south. See, so you see it's attracted. Similarly, the south is attracted to the north. Here you go. And so the poles of a magnet, so they are opposite poles of a magnet, and the opposite poles will attract. We just play around with this, right? So if I turn it around, you can see that they actually repel each other, right? I can show this very clearly if I try to levitate them, all right? So I've got a straw. So let me try and levitate the magnets to show you. Like that, okay? So I have to put the other way. So I've got the two facing sides of the ring magnet are opposite poles. So they repel each other, right? So like poles repel and unlike poles attract. So I'm going to try and put another one. I've got to make them repel. So I've got three. Should I make a fourth one? I do not know which side it is. Okay. Okay, wrong side. Wow. So I've got levitating magnets on this straw, and so the like poles are all facing each other. That's why they repel. Okay. I'm going to show you another way to show that they repel each other. I've got this, and I put the disc magnets with the like poles facing each other and taped to a plastic sheet, as well as held on by raffia strings, and you can see that they are repelling each other. Okay, so if I can even put a ruler through, and still they are repelling each other. You can see if I put them together, they repel each other, right? So this is the like poles repelling each other, all right? And for magnets, there are magnetic materials that they attract, as well as non-magnetic materials that they do not attract. So let's take a bar magnet here, okay, south pole. So let's try and attract the plastic straw and the ruler. Doesn't seem to work. And how about some coins? I've got some metal coins here, but you can see that, hey, not all metals are attracted to the magnet. How about these? Yeah, these are attracted to the magnet. Well, okay, so you can see usually it's the shiny ones, the shiny coins that are attracted to the magnet. So now we're going to do a very fun experiment. Okay, let's see. Put this aside. I'm going to build a magnetic tower. And I want to explore whether the magnetic force can pass through certain materials. Like in this case, I've got non-magnetic materials, like a piece of plastic as well as a piece of plastic as well as a piece of cardboard. Okay, we're going to try with the plastic first to see whether if, can you see? Oh, can you see? Okay, maybe I'll just hold it up. Can you see? I'm going to see whether if the magnetic force can pass through plastic. So I'm going to hold it this way, not touching the plastic. And I can see that, maybe I'll use a stronger magnet here. Here. Okay, stronger magnet. Whoa, I can see the coin attracted to the magnet, and the magnetic force is passing through the plastic material. Right? How about the cardboard? Does it work with the cardboard? Here. Okay, it's quite a thick piece of cardboard and very hard piece of cardboard. Oh, it actually does. If I'm not touching the cardboard, I can see that the magnetic force is passing through the cardboard to attract the coin. All right, now we're going to have a very fun experiment. We're going to build a tower. This is a magnetic tower. Okay, let's try again. Okay. So we're going to try with two magnets, these magnets, and we'll see how many of the coins we can attract. Can you see? 1, 2. How many do you think we can attract? 3. Oh, I think that's about it. Let's try. Oh, that's 3. If we add on the magnets, let's see whether if we can attract more. And I have here these very strong neodymium magnets. They're very, very powerful and strong. So if you have a pacemaker in your heart, it is quite dangerous. So you do not want this near your heart if you have a pacemaker. So let's try and make it really, really strong. So I've got quite a number of neodymium magnets. Let's see how many I can attract. 1, 2, 3, 4. Well, just now was 3. Now we've got 4. 5. Okay, I've got 2 more 5 cents. Do you think we can do it? Nope. I think that's about it. So we can attract about 5 coins, very heavy coins. All right. Okay. So now we're going to see. We're moving on to see some of the applications of magnets. So knowing that, some of the properties, it attracts certain materials. These are magnetic materials, and it doesn't attract the non-magnetic materials. And we also learned that magnets, like poles can repel, unlike poles attract. Let's see whether if we can make use of them in our daily lives. Okay, so put this aside. I have here a maglev train set. So it's magnetic levitation train, and this train can be found in Japan, I think even in Shanghai, China. So they move at very fast speeds because there is no friction. You see here, when I try to move, it will eventually come to a stop. This train has got some magnetic strips on the bottom. Okay, so these are also magnetic tracks, and when I put them on, you can actually see that it is suspended. So I can press it down and then it repels and is suspended. So when I try to move it from one end of the track to the other, whoa, it actually moves very fast and very smoothly. And that's what happens to maglev trains in real life. They move very fast, incredible speeds, because they are not touching, they're actually levitating over the rails. Whereas if you have got like that, you can see there's frictional force, right? So this is a case of an application of magnets in real life, which allows you to travel from like Osaka to Tokyo in a very short time. All right. Next, we're going to show another application of magnets. This one we showed the application of repelling, right? Repelling. Next, we're going to show an application that has to do with attraction of magnets. Next, I'm going to make an electromagnet. So an electromagnet is made using electrical source like a battery, and you need to get a material that's magnetic. In this case, it's an iron nail, and I coil wire around it. So when I let electricity pass through the wires that's coiled around the iron nail becomes a temporary magnet, and this magnet would then be able to pick up magnetic materials. And you use this electromagnet in a junkyard to separate magnetic materials like certain metals from the non-magnetic materials. So the metals can be used to make stuff again. You melt it, make something else, and then you're recycling the metal. Okay, so I'm going to make it, and I'm going to pretend I'm in a junkyard and see whether if I can separate the magnetic materials from the non-magnetic materials. So what I have here on this piece of paper, I've got aluminum foil. Aluminum foil. Do you think it is a magnetic material? It's a metal. I've got a piece of plastic. Tiny piece of plastic here. A piece of plastic. And I've got a piece of cardboard. Okay. So I'm going to see which materials can be picked up by the electromagnet. Okay. So I'll connect the wires to the terminals of the battery, and I'm wearing gloves because sometimes the wires can get quite hot. So I just want to protect myself from getting uncomfortable. Okay, let's see. Oh, I managed to pick up a few. Let's try and do it facing the other way. Okay, I managed to pick up, all the staples, but unfortunately, I'm not able to pick up the aluminum foil, plastic, or cardboard. Okay, so we have found out that even though aluminum foil is a metal, it is not magnetic because it's not able to be picked up by a magnet. And then you can see that now the magnet, previously electromagnet, now when it's not connected to the battery, it does not pick up the staples anymore. Okay, so this is a good way to separate materials that are magnetic and materials that are not magnetic. So next, we are going to see whether can we separate the magnetic from the non-magnetic material of this magnetic putty. So what I have in here is kind of a slime material, and mixed with the slime are iron filings. So iron filings are magnetic, something like the staples, and they're all mixed into this slime. So it's like a magnetic putty. So we're going to see if we can separate out the iron filings. What do you think? Do you think we can separate out the iron filings from this slime? So I'm going to use a very strong neodymium magnet, okay? And I'll try and see if I can separate this. Okay, quite interestingly, you can see that the iron filings are attracted to the neodymium magnet, and it's kind of moving with the magnet, and it's kind of like a dancing snake. Da 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 da. So, but it is unfortunately unable to separate out the iron filings from the slime. Okay, so in this case, it is not able to. All right. And for our last little activity, we're going to make a magnetic toy car. Alright, so I think packed with your materials, I've got this. I've got either a plastic sheet, and in fact at home you can try it on your own too. Without this plastic sheet, you can always use a piece of cardboard, okay? Then you need Scotch tape. Okay, in your pack you may have 2 straws. So we're going to make the wheels of the toy car. You can easily take that down. Make sure the straws are parallel. Okay, so make sure the straws are parallel. Parallel means they're like a train track. They never meet, they're parallel. They will never meet, okay, no matter how much you extend it. So they're parallel. So this will form the bottom of your toy car. Next, we use the satay sticks, okay, and you're given 4 pieces of plastic wheels where a hole has been poked through the center. Okay, so we are going to first we poke through like this, okay. Then you insert it through the plastic straw and insert the other wheel. Then you do the same with the other 2 wheels. Insert first. Okay, go through the straw and insert. Right. So now you test whether if they move. Okay, they move. So this is well done. And on the other side, we're going to make a magnetic toy car, which means that it will be propelled. It will be caused to move by magnetic force. So just now I have the 2 disc magnets. So I will put one here and tape it down. Then I'll take the chopstick and tape the other disc magnet. Now, you can actually try and see if it works. See, it works very well by repelling. But if you use the other side, which is the which will attract it, you'll find that it's not going to work very well because you have a toy car stuck to your magnet. So you use the repelling side to move it, to repel it. So this is a push force, and this one is a pull force, right? So a force is a push or pull. So we're going to use a push force. So we're going to stick this to the chopstick. So you have a little wand, and then you can make your toy car move. And if you make a few of these, you can have a little race with your friends. Okay, so that's it for today's lesson. Let's go through the worksheets. On page 1, remember I did a magnetic tower experiment, and we also found out that magnetism passes through the plastic and wooden materials that are used to test. So anytime you can stop, you can pause the video to write down the answers. Okay, and then we go to this page. Page 2, I made a magnet suspend over another by using a stiff plastic sheet, and I had 2 magnets facing each other, and the other one was held in place by raffia string, and we found that they were repelling. So the sides of the disc magnets facing each other are, is it like or unlike poles? because they repel, and we know that like poles repel, the answer is like. Okay. Next, we went into the application of magnets, where we looked at a maglev train activity, and we also watched how an electromagnet would work. And during the experiment, we saw what objects were attracted to the electromagnet. So in this case, was it the paper or cardboard, aluminum foil, plastic, piece of plastic, or the iron staples? So we found that only the iron staples were attracted. So you may circle this. And while most metals are magnetic, which metal is not magnetic? And we could see between aluminium and iron, these two are metals, but the aluminium was not attracted to the magnet. And so we have a picture of an electromagnet in a junkyard separating the metal pieces, the magnetic material, from the non-magnetic materials to be recycled. Either it can be melted down and made into other new objects. We could separate the magnetic from non-magnetic materials in a junkyard, but we were not able to separate the iron foulings from the slime of this magnetic putty. So does it attract? So does the neodymium magnet, very strong magnet, attract the iron foulings in the putty? Yes, it was attracted, which is why we could see the slime moving when we moved it. But does it separate the iron foulings from the slime? No, it did not. And finally, we made a magnetic toy car, and we could see that magnetism acts over a distance. We use the repelling force of the magnets to move the toy car. Let's take a look at the question on page 5. A U-shaped magnet was cut into half as shown below. Cut into half. One broken part of the magnet was placed in a tray of iron foulings. So iron foulings are like powder, iron powder. So these are magnetic materials. It's a magnetic material. Which diagram shows the positions of the iron foulings when it was taken out of the tray? So here it shows that it's attracted to the north pole. Here it's attracted to the broken end, and this is attracted to both. So what happens when a U-shaped magnet is broken? What happens to this end? Okay, so this end is north, and we find that it is attracted to the south, so it's north. Then the other end, we find that the other end is attracted to the north. So this broken end has become a south pole, so it is also able to attract. So it's also able to attract magnetic materials like iron foulings, just like here. Okay, and in the middle here, well, not so much. It's usually the poles of the magnet that are strongest. So the answer should be 3. Okay, I just want to explore also about explore the strength of the magnet, and we find that the magnet is strongest at the poles and not so strong in the middle. Here I've got 2 5-cent coins. We can see that it is readily attracted to the poles of the magnet, the north and south poles, but if you put the middle part, it's not as strong. Similarly, for a bar magnet, it is strong at the poles, but not so strong in the center part. The middle of the magnet is not so strong. Okay, so we learned something. I hope you have learned something. Thank you for joining me for this lesson.